Having obtained the x and y components of the velocity of ball 1 and ball 2 after collision, we can multiply the velocities by the masses of the two balls to get the momentum of each ball after collision. So we have a momentum 1 after collision and a momentum 2 after collision. Now these momenta can be added. We simply take the first momentum and we start it from some point. Put the tail of the vector at one point, the head at another. And we take the second momentum and we put it tail to head with the first. Then the total of these two momenta is simply the momentum that we get if we go from the left-hand side of the first, from the starting point of the first vector to the end point of the second. Now, that momentum, the total momentum after collision, should be equal to the total momentum before collision. Since the total momentum before collision was all in the positive x direction, or the horizontal direction as we look at this figure, but in the x direction, then the total momentum after should be in the x direction. This tells us that the y component of this momentum and the y component of this momentum should be equal and opposite. If we look a little more closely at the momentum situation, say again we have the momentum of the first and the momentum of the second ball after collision. The momentum of the first can be broken into the y and x component of that momentum, again with a rectangle here representing or rectangle being used to see what the y and x components are. And the second momentum is a result of an x and a y component. Again, these x and y components are actually found from the x and y components of the velocities multiplied by the mass of the respective ball. So the first momentum is obtained from the x velocity of the first ball times its mass, and the y velocity of the first ball times its mass by drawing this rectangle and getting the diagonal. Second ball similarly. To add the components, we represent all the components as if they're acting at one point. Now this is analogous to the way we think of forces. We have a y momentum in this direction, a y momentum in this direction. Well, if we had forces pulling this way and this way, and if they were equal and opposite, they'd cancel out and there'd be no y component. And if we had two x forces, one pulling this hard and one pulling this hard, this one obviously pulling harder than this because the vector's longer, then we'd add these two. Okay, they would sum up to a larger x component. So by looking at this picture and not thinking of forces now, but thinking of momenta, but adding them as we would if they were forces, we see that we get a total x momentum that's larger than either of these, actually equal to the sum. Now I didn't really draw that vector long enough. It should probably be out to about here to get the sum of these two. You can correct that in your imagination. And of course we have a 0 y component if the y components are in fact equal and opposite. Now when we do this experiment, we're not going to get this ideal result. Most likely our y components will be pretty small, pretty much equal and opposite. The total will be pretty small, but it won't be exactly 0. These things won't be exactly equal and opposite. And we'll have two x momenta, which we can compare with the velocity or the momentum of the ball before collision. Remember, the one moving ball before collision will presumably have a velocity that we can obtain by measuring its motion down the ramp, by timing its motion down a ramp or something. And then we can compare the total momentum before with the total momentum after.